Reduce arc flash and create a safer inspection? That's where airborne ultrasound comes in. I'm Anthony, editor of Electrical Business Magazine. It's great to see we have registrants from Alberta, British Columbia, Ontario, Quebec, Saskatchewan, and the Northwest Territories. Welcome to you all to this webinar on airborne ultrasound for electrical reliability. Your speaker today is Certified Maintenance and Reliability Pro Sean Miller of UE Systems. Sean will show you how airborne ultrasound can be used on open or enclosed systems to detect and analyze corona, tracking and arcing, and he'll explain how airborne ultrasound and infrared thermography complement each other so you can level up your electrical maintenance and reliability program. After Sean's formal presentation, there will be some time for Q&A before we wrap things up. Just type your questions into the questions window on your webinar control panel at any time during the presentation, not the chat window, the questions window, and we'll save them for the end. Oh, and so I don't forget, please be sure to sign up for our November webinar, where construction law expert and legal desk columnist Dan Leduc will unpack the results of Ontario's Construction Lien Act review report, and he'll explain the possible ramifications for you and your business, such as prompt payment. Visit ebmag.com/webinars. And with that, I'll hand it over to Sean Miller. Sean.
For everybody I know who's in Ontario today, I apologize that we're doing this webinar. The weather is too nice to be sitting inside an office to be doing this. However, I got to come out to impress. So I'm here, and thanks to Electrical Business Magazine for having me. And hopefully today everyone can learn something new when it comes to airborne ultrasound for electrical reliability. So with that, let's get started. And it's funny doing this because I'm so used to having an audience, and now I just have me. So this is just seeing me here. It's actually kind of funny. So today we're going to talk about, for the most part, obviously ultrasound in the electrical reliability realm. And I'm going to go through a few things today. First of all, what is airborne and structure-borne ultrasound? You know, that's a big question I get asked a lot because we get confused with a lot of different ultrasounds. And because of that, I want to make sure that we understand, kind of give you a little ultrasound 101 and where we fit into that type of technology. Secondly, we're going to talk about why incorporate ultrasound and the benefits of ultrasound into electrical maintenance program, or maybe even other applications such as rotating equipment, etc. But we're going to focus mainly on electrical today. That being said, where it can be applied, as well as we're going to talk about electrical sound analysis. That is a key factor when it comes to ultrasound, and that gives us an advantage over some technologies, but yet being complementary, and how we can actually diagnose what we're looking at, listening to, and take it from a question mark to, hey, this is what we're seeing in these particular electrical assets. And of course, a couple case studies will be floating through this as well as I go through it. So that being said, let's get started and move into what I generally start off with is this header here, which is the generic divisions of ultrasound. And why I start with this is because, again, when people think about ultrasound, the first thing everyone thinks about, 99% of people say babies. They're looking for babies. They're looking to look at the baby in the womb, and that's what ultrasound is. And that is a division of ultrasound. You can see that in this first division here that it's a pulse echo. As a pulse echo ultrasound, where really we have one transducer that emits a signal where this is the pulse, and the echo comes back off of the fetus in this case and gives us a picture of a healthy baby, a boy, girl, etc., etc. So that's really where that division falls under. So we are not a technology that's going to find babies. And if you are using our technology and you're finding babies, I don't know what you're doing, but we need to chat. So at the end of the day, though, pulse echo is a very known technology, ultrasound technology, because it's known for the non-destructive testing ultrasound, where they would look for thickness measurements, maybe if the welds are good, or if there's cracks in material. So that is pulse echo. Keep in mind that that technology or that type of division of ultrasound has to emit a signal for something to happen. The second division that you see in the middle there, which is called power ultrasound, generally we experience that on a regular basis. A lot of companies I deal with have ultrasonic cleaners. That is a great example of power ultrasound. Same thing when we clean our jewelry, that's ultrasonic, that's power ultrasound as well. The other factions we have with power ultrasound is that we go to sports therapy to use ultrasound. We have ultrasound used on our muscles, our bodies, to reduce inflammation and scar tissue, etc. We go to the dentist and they're using ultrasound now to remove calculus and tartar from our teeth. So again, a different division than we do, and as well, just like the first division, it has to emit a signal for something to happen. And then there's the last division, which is us, and this is airborne, structure-borne ultrasound. Obviously, this is the title of the webinar today. And unfortunately, we're the longest name that we have on the generic divisions, but we are a different ultrasound than the rest of them. One thing that we are considered is that we are passive ultrasound. So we don't send anything out. We are only receiving signals. And as you can see here, we receive them through an airborne medium or a structure-borne medium. Okay, so if you didn't understand that, there are 3 generic divisions of ultrasound, and we are one of them, obviously, and there are other divisions that can be used in different ways. So continuing on with some theory here, just a little 101 for everybody out there. This our ultrasound, as I mentioned before, detects frequencies between 20 kilohertz to 100 kilohertz. If we're familiar with our human range of hearing, it actually goes from 20 hertz up to 20,000 hertz, or 20 hertz up to 20 kilohertz. That's the human range of hearing, and that's obviously low frequency or considered audible frequencies. Ultrasound starts at 20 kilohertz and goes above that, and that is considered high frequency sound. As I mentioned on the previous slide, our ultrasound does not transmit high frequencies whatsoever. We receive frequencies only, and how we receive them is basically in the line right below it. We receive high frequencies from either turbulent flow and or friction. And when I'm training a lot of companies, I ask them that question, what in your facility would give off turbulent flow? And a lot of them come back saying compressed air leaks or gas leaks, and that's exactly correct. The collisions of electrons that occur, or additions in the electron and collisions that happen in the atom that create ionization, create turbulent flow, which allows us to hear the electrical emissions, which I'll be talking about in a little while here. And then the other thing we detect is friction. So friction obviously is in a lot of areas in a lot of facilities or places that I go to, and obviously people recognize that as coming from rotating equipment. So bearings give off friction, and I generally ask the question, do good bearings give off friction? And the answer is yes. The thing is, when bearings get worse or they tend to start wearing out, or there's more lack of lubrication or lubrication, then we have more friction, so we can measure that. Our instruments heterodyne these high frequency sounds, and heterodyne is just a very fancy word for saying that it translates these high frequencies down to an audible range, so now we can hear them. Otherwise, we can't hear high frequency ranges because they're above our hearing level. So the heterodyning happens in the instruments that allows us to then audibly pick up these sounds in our headphones while it's being translated down to a range that we can hear. We use structure-borne mediums and solids, so like a motor, maybe a gearbox, maybe things like that to hear through, pipes, valves, etc. We use also airborne mediums like gases to detect ultrasonic emissions, and again that comes from turbulent flow and or friction. Ultrasound is very fast and accurate and is directional, which is really an important thing to understand. If you can imagine your own hearing or how we hear as human beings, our hearing is described as omnidirectional, multidirectional. We don't know generally where the source is coming from, and I usually ask that question to people in facilities where I'm asking them to find me a compressed air leak with their ears, and it's very difficult to do. Where with ultrasound, it's extremely directional. We pinpoint, we can isolate exactly where the signal is coming from. With ultrasound too, we can trend and record data as well as sounds, which we're going to discuss in a little while here, and or even troubleshoot. I've been up to many utilities in the last few months, and we were just troubleshooting some of their insulators, some of their bushings, and some of their substations to find where the tracking is, or if there's corona, et cetera, But you're also going to learn there's multiple applications to ultrasound as well. And we're mainly going to discuss the electrical side. On that side of the coin, though, there are 3 primary application groups that we work off of. Number 1 is leak detection, and for the most part, most companies understand that part of ultrasound when they say, oh yeah, you can find air leaks. And it's true, we can find compressed air and gases as long as they're turbulent, and we can use them, we can look at them either in a pressure situation, so leaks coming to atmosphere, or a vacuum where they're going away from the atmosphere. We can also qualify. What I mean by that is we can actually find exactly where the leak is coming from, but then also we can give a cost to those leaks. And for some of us who are in some areas where we're being charged high for our electrical bills now, our kilowatt per hour is being driven up. This becomes a very important tool, a cost-saving tool to help reduce our kilowatt per hour and, of course, bring in more energy conservation to our facilities. I'll go to the side on the right where we're talking about mechanical stuff. So on the mechanical side, we can also do valves, steam traps, and hydraulics. And with bearings, we can detect bearing defects and lubrication issues in motors, pumps, and gearboxes. So these are a lot of things that we can focus ultrasound on. But today, we're going to focus on the electrical inspection. And just to give a little segue, we're going to be looking at and being able to detect corona, tracking, and arcing, or even maybe a mechanical vibration or looseness in an electrical asset. We can do this on open or enclosed systems as well, and I'm going to explain more about that, but just to give you a little bit of a leeway here, we do not have to open up panels to actually listen for electrical emissions in ultrasound. So hopefully some of you who are hearing this for the first time, that may have perked your ears a little bit here, because this allows us to reduce a lot of any type of unsafe practices or even maybe unsafe inspections. Okay? So one thing I generally talk about here, and I know a lot of people out there, whether it's in the electrical world, the reliability world, etc., you name it, they always say, you know, I have an infrared. I'll just need infrared for to do electrical inspection, right? And I'm like, no, it's not the answer. Here's a little video I put together. I'm a golfer, so the reason why this is on here is to kind of give a little humorous anecdote to what we're talking about here. But can one technology do it all? Do all the failure modes we're looking at? No, it can't. And here's the video.
New club? New set. Check it out. This one's forged titanium. Real bruiser. I've also got one with tungsten. This one here, 12 hosel adjustments. 12.
But they're all drivers.
Yeah. That's all I need, right?
So you get the idea where here's a guy going out just using a driver or drivers to play golf with, where we have other options in our golf bag to use. And the same holds true with the technologies that we use. We have a lot of different options to use on different failure modes. And if you're not familiar with what a failure mode is, it's basically how can something fail? What ways can it fail? And in the electrical world, there are many ways. And if one technology is all you're using, you're missing the boat on other failure modes. And of course, and maybe even losing some competitive edge to your competitors as well. So hopefully you enjoyed that. But I want to take a little time now to talk about the electrical inspection with airborne ultrasound. So as I mentioned before, we are hearing the ionization from the collision or addition of electrons in the atom, and this itself causes turbulent flow, which allows us to hear the ultrasound in electrical assets. We can use ultrasound on any voltage, low, medium, and high voltages. So again, why the utilities are using this is because of this reason. We can detect corona, tracking, and arcing. So what I mean by that is not only detect, we can analyze what we're looking at. So you can see the picture of the gentleman here doing scans with our equipment, and we can literally look at those insulators on that tower there and say, you know what I'm hearing electrical emission there, and what that emission is either corona or tracking or arcing. So we can diagnose that. Maybe we have an issue of a dry transformer where it is a winding is loose, or we have some delamination of the winding causing a vibration versus actual electrical emission, such as tracking or arcing or corona. So we can actually use our ultrasound technology and software to determine that. As I mentioned before, it can be used on open systems or enclosed systems. Open systems like insulators and substations, bushings, bus bars, etc., and can be used on closed systems like switchgear, MCCs, transformers, you name it, that can be used. And again, the name of the game here is that it's non-intrusive. We are not placing any part of the instrument inside an electrical asset, panel, or anything. We are away from it in safe distances, which helps us create a safer electrical practice, as you can see here. Reduces arc flash and shock hazards as well, and can be used as a best practice with infrared. So before opening up a panel, maybe we're trying to do an infrared scan, but we want to make sure that that panel is safe to open up. We can do an ultrasonic scan to determine if there's anything going on behind that panel or not, and if there isn't, then we can safely open it up with infrared as you get your PPE on. Okay. So hopefully we're still on the same page here, and we're still moving along here. And I apologize again for the delay. One thing I like to show people is with a lot of electrical gurus that I deal with in Canada, this became a big deal back in December of 2013 when CSA Z463 was introduced, which obviously talks about electrical maintenance and safety electrical maintenance safety practices for Canada. And you can see that in CSA Z463, ultrasound is actually mentioned as this, and this is becoming an official standard. So an important thing about this is that we are actually a recognized technology to be used on online testing, meaning that if you're not going to test it on, if you're going to test it online, even though CSA Z462 says it's better to test it offline, but when we have to, we can use our technology along with infrared to diagnose problems with those electrical assets. Okay, so our common electrical applications. It's very simply put. We've got the standard stuff. Ultrasound detects discharges and emissions on all voltages, as I mentioned before. We can detect arcing and diagnose that it's arcing. We can detect tracking and again diagnose that it's tracking, or corona or PD as well. All right, we can do this in switchgear, insulators, transformers, dry and oil-filled arresters, potheads, MCCs, breakers, and again, as I mentioned before, we can determine whether this is actually an electrical emission versus a mechanical vibration or looseness that's happening in an asset. Okay. So how does ultrasound work? How do we do this? Well, we're using this technology to look for a problem and hear a problem. And when we hear something, we then take our technology and we record the sounds to diagnose what we're hearing. If we don't do that, it becomes a little subjective. So we're listening to a panel that ends up being, there's a sound in there. First of all, do we know it's electrical or mechanical? And secondly, if it is electrical, what is going on behind there? Can we open it up safely without testing the waters, if you'd say? So we're able to do this, and we're going to go through these analysis of sounds through our software to understand, you know, what are we looking at here? What are we seeing here that these sounds make in the spectral analysis? So electrical physics for ultrasound inspections. When the electrical discharge in the air occurs, ionization of the surrounding air begins, which obviously is where we're getting the turbulence coming from. This generates a separation of electrons that forms ions by collision or addition to the surrounding atoms. This process generates ultrasound, and again, as I mentioned, it creates turbulent flow, which allows us to hear these sounds. Again, doesn't matter what voltage. So as we move forward here, we're looking at ionization again and continuing on. So ionization, which is obviously creating turbulence, forms an ozone and nitrogen oxides, and these combine with moisture and produce nitric acid. We all know any type of acid is not a good thing. And in this case, electrical dielectrics is definitely not a good thing because the nitric acid is destructive to these dielectrics and compositions resulting in corrosion. And from the corrosion, you can see here that the shield in between these bus bars here, we can see that we have white residue happening there, which there's direct corrosion happening there to that particular piece there. With corona, and as I said, this is something that is you know, when I talk to people, I go to a lot of facilities who are electricians, they're obviously thinking corona is our beer, we're listening to the beer, so we're hearing beers, or seeing beer, or whatever the case. That's not the case in the electrical world. Corona is basically a lower electrical discharge around conductors. And it basically happens when the surrounding air is stressed beyond its ionization point, but it doesn't develop flashover. So what we're seeing here is just a complete ionization occurring. And from there, we were able to hear that. I guarantee you, everybody outside who was walked by maybe lines in the on the towers there, or walked by you know, the pots, etc., that are around the area of your housing area, that you're going to hear corona when it's snowing, when it's raining, etc. When there's more moisture in the air, you're going to hear that naturally occurring. One thing corona does not do, it does not occur below 1,000 volts. So anything that is happening below 1,000 volts, you can guarantee corona will not be present. From there, corona also seeks a path to ground, and that's key because it's seeking the path to ground, not finding any path yet. It's still just seeking a path. And as we go into our first electrical emission here, we're looking at corona having this type of sound. Now, I hope that came through clearly, but it was a very, very obvious frying bacon consistent sound that's being heard there. And what we're seeing here is when we record this on our instruments, we bring it back into a spectral analysis, in this case an FFT, or fast Fourier for the long version. And what we're seeing here is obviously a distinct 60 Hertz harmonic. However, just because it's 60 Hertz doesn't necessarily mean it's corona. And it doesn't even necessarily mean it's tracking, or sorry, it's an electrical emission. It's just saying that 60 Hertz are present there. But to diagnose or understand that's actually electrical emission, which is what we would do in the FFT format here, you would look in between the 60 Hertz, and you can see the annotation there that says that the 60 Hertz, the frequency content that happens in between the 60 Hertz indicates that this is an electrical emission. So the 60 Hertz are important to note. However, going forward, it's seeing what's happening in between the 60 hertz that gives us a clear indication whether it's electrical versus a mechanical issue. All right. As we see this, we then know it's electrical, and then our next step is to take it to the next level into our time domain spectrum here. So we go from FFT into time domain, and we start to see and hear the same sound. Again, the same buzzing sound. This is what we're listening to. And by examining the time domain, you're going to see that we have very uniform spacing going on with some elongated negative amplitudes. And from that, we can deduce that what we're listening to is corona or seeing corona. So you can see right away that we're using the patterns that we're seeing of the discharges in the time series to determine, hey, what are we looking at here? What are we seeing? And that's important because now we can take this to a diagnosis level, whereas with just listening, we wouldn't know what we're listening to. So you can see that we have very even discharges, very evenly spaced discharges. We do have some longer lengths on the bottom of the bottom part of the amplitude of the spectrum there. That gives us our indication that this is that this is actually corona, and that's important to know. So now we can use this because there are very few technologies that can detect corona. Infrared is a great technology, but you know, working with all my friends at FLIR in that, they'll tell you, and most infrared cameras will not see corona because it does not create enough heat. It's just ionizing. Ionization does not create heat. Therefore, it is not a good failure mode for IR to detect. But again, this is why we use multiple technologies, right? So going forward, the reason why we diagnose this as corona is it has to do with where the discharges happen in the sine wave. And the discharges here you can see are happening on the negative peak of the sine wave. Those negative peaks are where ionization occur the most, which gives us our even spacing. So if you look at where the arrows are pointing and where the discharges are happening on the sine wave, that's the reason why our corona time series is has evenly spaced discharges or events, because of where the ionization is occurring. And that allows us to then diagnose that this is corona. And you can see that we, just as it explains in the bottom here, that the discharges are only at the positive and positive negative peaks of the sine wave, okay? Not the positive side. It's at the negative peaks of the sine wave. So that was a bit of a misnomer down there. I apologize. Okay, so that's the first analysis we're looking at. Then the next one here is where we have a mechanical vibration. So I showed you a couple slides back that corona had a 60 hertz harmonic showing up, but then also had content in between. Well, if you look at the spectrum on the left side here, we start to see we have 60 hertz, and even though I didn't mark them off, they are at 60 hertz, but our 120s are more dominant, but still giving us a 60 hertz harmonic. But note the lack of frequency content in between the peaks. There is no content where we saw with corona or an electrical discharge. And that's our indication right there to say this is a mechanical vibration. And this is one example of a mechanical vibration sound. Okay, and you can understand that. That would probably fool a lot of people. Let me just go back to my slides here. That would fool a lot of people because they would think, oh, this is an electrical problem, where in fact it's not. And this was taken off of a dry transformer. And what we're seeing here is the fact that we have a 60 hertz harmonic showing up, and we have dominant 120s without content in between. So right now we know it's a mechanical vibration, but where is it coming from? It's the 120s. Those 120s that are actually higher than the 60 hertz, they are the clear-cut factor to tell us where it's coming from. And in fact, the 120s are a clear indication that this is happening at the core of a transformer. So this actually is a loose winding happening in the transformer, a dry transformer, obviously. So again, I know not probably as clear as it could be if I could sit down with you for anybody for hours to talk about this. But if we look at the indication here, the lack of frequency content in between these peaks, the peaks and the harmonics there, indicate that it is not a mechanical, it's a mechanical issue rather than a electrical emission. Okay. Going into our next one, we have tracking, and obviously tracking has now progressed further. Where tracking has found a low current pathway, and that low current pathway has given us is going to give us a different sound, because that low current pathway has now developed into some flashover. And when we say flashover, we're obviously referring to arcing. In this case, we would sometimes call it baby arcing when it comes to tracking, and it can sound a lot like this. I'm not sure if you could note or pick out those little pops and cracks that were going on inside that sound wave there, but you get the idea that those pops and cracks were not evident with the corona. It was more like a buzz happening, where now we have a buzz plus this popping and crackling. And the reason why that's happening is going to be explained shortly, but basically it's the flash, there's that flashover starting to occur, that low current pathway that's allowing that to happen. You notice in the spectrum here on the visual picture that we're losing our harmonics. Before we had a lot of 60 hertz showing up, very rich 60 hertz harmonics. But as we continue down the spectrum and we go further away, we start to lose those harmonics, and that becomes evident because the flashover is now taking over our rich 60 hertz. We don't lose our line frequency unless something is off. So in this case, the actual flashover that's occurring, causing those pops, is covering up our before rich 60 hertz harmonics, and that's why we're starting to see a difference. However, there is still frequency content in between the harmonics that we see here, so that's a clear indication that this still is an electrical emission. And as we move from the frequency domain, which is the FFT, onto the time series, we can see the big difference between corona and now what we're seeing here is tracking. Corona was a very, very evenly spaced harmonic with a lot more negatives on the end, where now we're seeing non-uniform spacing between discharges, as well as positive and negative peaks going on in the amplitude to indicate that we've got a lot more flashover going on. And that flashover is going to create uneven spacing because, as we see on the next slide here, the flashover can go wherever it wants to on the positive part of the sine wave, and that's what gives us our even spacing, noted by the red lines that are on the sine wave here. So when we have the next stage of tracking, just to summarize here, there's a low current pathway to ground across an insulator, so that discharge does not have to take place at the peak of the waveform. It therefore can happen anywhere on the positive portion of the cycle. They correspond to that popping noise that we were hearing. That's exactly what we're hearing. And they end up becoming more non-uniform and very narrow peaks. And those narrow peaks and non-uniform patterns that we see are a clear indication of that this is tracking. All right. And of course, moving on to the big one that we do not want to experience or ever want to be near, but it's the arcing one, and I'll play this for you. Okay, and with that, you can obviously hear that there's a lack of ionization occurring now, where in the last two discharges we heard ionization, but all we're hearing now are the discharges. So that's a big key indicator of sound analysis. But as we look at the spectrum, we start to see the loss of harmonics again, much like with tracking. So we're not seeing 60 hertz showing up, but we do have content in between our harmonics. Just they're not actually evenly spaced like we saw before in some of our other electrical emissions that was occurring before. As we go forward into the time series, now we start to really understand why this is arcing, because now these events are very long and drawn out. They're very violent stops and starts that occur, where with tracking, what we had with tracking was a building of intensity and then discharge, a build of intensity then discharge. These become, in the arcing realm here, it becomes a very abrupt stops and starts and very violent stops and starts. And therefore, by looking at the time series, we can see the larger events that are occurring, the lack of ionization in between the events as well, and we clearly hear the events or the discharges taking place throughout the sound file as well as in the time series here. So I hope that gives a bit of an idea of what we're looking at here, because this is how we're able to take, looking or listening to something and take it from listening and just hearing something that's subjective to now to something where we can analyze and show people that, what, I'm looking at that insulator, and what you have that insulator there is clear-cut tracking. And I've been with many of the eastern utilities this past summer, and we've been doing a lot of this testing across their substations. And you know what? We've been finding a lot of tracking and corona at their substations that where they've just recently replaced or cleaned something. Okay. So again, why is arcing why does it have that type of pattern? It's the same thing as tracking, except the fact that instead of being smaller and narrower events or discharges like they were before, we now have larger events, which is noted by the big red bar that's sitting there in the middle of the last part of the sine wave there. So again, they are, when you have arcing, the discharge can go to ground across an insulator. Basically, that path does not require high potential. So this is a burst of energy that we can hear, and of course the buzzing sound that we heard, as I mentioned before, with ionization or with corona and tracking, that no longer exists now. And all we're hearing now are these violent stops and starts, and they're seen as wide peaks, these violent stops and starts in the time series, and that's why they look like they do. All right. So, you know, how do we take their equipment now? So we know what the sounds are, but how do we do the scan? What are we doing? So here's an example here where we're doing airborne testing, where we would scan and take our equipment and scan around the seams or even the top or the air vents of an electrical panel, an asset, and scan around those seals or door and air vents of the enclosure, because high frequency sound will not penetrate through solid objects, but when we have a path of least resistance, what we're seeing here with the seals or the air vents, it will escape through that, and we can easily point out that that there's a sound in there. We would use a 40 kilohertz frequency based on ISO standards as well to focus and narrow down the inspection area. All right. So that's one way. There's another way, of course, where we can get into longer ranges. And one of the big questions I get is, how far can you actually go, Sean? And I said, our equipment can reach up to about 150 feet away using the parabolic dish that you see on the left there, and to a 5-degree radius. The one to the right is our long-range module, where we can go up to about 100 feet away with a 10-degree radius, and that's commonly used in a lot of the substations that we go out to. But when we're dealing with the high towers, like we are on the left, the parabolic dish becomes a very powerful tool to use and pinpoint. So we can literally pinpoint which insulator is causing the problem, and then we can say that insulator is either tracking, has arcing, or maybe corona there, and that's the key there. We're able to diagnose these things, and that's the big benefit, right? There's a couple case studies showing up here. There's one we have that's an MCC that you know, with it being enclosed, it's hard to determine something. And people say to me, well, I can get IR windows. You can, and they're great technology. We know a lot of IR companies and IR window manufacturers who actually make ultrasonic windows as well. You know, but at the same time, it's hard to if you don't have those windows, you can't use them. You can't diagnose unless you open up the panel. So with a closed cabinet, it can be difficult to determine if there's a problem inside, and that can lead to catastrophic problems. But what we're able to do is scan, and you can see in the diagram on the left there that we were able to scan through the air vent there, and this is what we heard inside this particular NCC. So that's pretty violent, and we were able to pick that up. You can see the results of that, the manifestation of that, those sounds on the right there with the pictures that you saw, or that sound that you heard. You can see clearly the burnt carbon, the burning that's happening there from the arcs that are going on. We were able to diagnose that, yes, this was arcing that we were seeing in this particular MCC. All right. Inspection of dry transformers, again, we talked about earlier, can be hard to do. Components are well enclosed, and it can make for sometimes impossible infrared inspection, unfortunately. But we can scan that air vent, and we can determine if something's going on before, obviously, a problem can occur. Now, there is a story about this particular, not this particular one, but there a transformer where this was happening years ago from one of our customers, where he got the call to say, you know what, we got a problem with this with our transformer. Can you analyze the sounds for us? So our electrical engineer in New York diagnosed this sound, and it literally was arcing. And he told the guy, listen, it's arcing. And unfortunately, it was a Friday afternoon in the summertime, and they left it until Monday, and hopefully nothing was going to happen. But unfortunately, on Sunday, that's what happened. So it actually went catastrophic. It went completely full out arc flash, and of course there was a danger of lives, and there was a danger of people getting hurt and injured, but also the money side as well. Obviously, it's going to cost a lot more money now had they not shut it, unless they would shut it down on the Friday before and actually done a repair on it or fix it up or replace it, whatever the case would have been. But just an interesting case study. I wasn't present for it, but I know this story from our company. Just very interesting. But again, we diagnosed the problem, and we were able to reduce that problem going forward. But unfortunately, what happened was it wasn't managed. So I have another case study here from northern BC. This was at a company called Eurocam Pulp and Paper, which is no longer in business, unfortunately. But they had a very interesting call where they had a 13.8 kV circuit breaker. And what was happening was there was actual audible noise coming from that. They could hear the noise, but their first inkling was to go out and, what are we going to do? Take the infrared camera out. But unfortunately, the infrared didn't see anything. There was no temperature change. There was nothing that was indicating a huge problem. And then what they did was they then took out our ultrasonic detector and recorded the sound and came back and diagnosed it as severe tracking. And what was happening was ultrasound was pinpointed and isolated the signal between the bus bar and the corona ring, and this was happening due to a bent metal tabs on the corona ring. It was causing this tracking going on. It was basically in the process of failure when it was first found. It was tracking, but within a couple of days later on, they went back. And they actually did another scan. It actually progressed into arcing at that point, where it was pitting on the bus bar. And so what they did was, when they detected it, they actually shut it down right away. And when they did do that, there was some big benefits there. Number one, no one was hurt. And we're going to talk about safety more than anything else. No one was hurt in this particular case study, and they were down only for 1 day at a loss of $750,000 for that day. But what they noted to me was, if it had gone catastrophic in that circuit breaker, there would have been a lot more issues happening, and they would have been down for approximately 2 weeks at $750,000 a day. The money is nice, but what this really boils down to is that we were able to help them. They were able to produce a safer environment. No one was hurt. They shut it down in time, and they were able to then do the replacements in due time so they can get up and running again. Okay. Another case study I had was a Slave Lake plant up in obviously northern Alberta, and you can see that they basically, the plant itself had sent me this file, and they started smelling some strong odors from this particular dry transformer. In this case, they thought they were hearing or something was going on. There was some severe tracking, but when we looked at it, when they sent the recording to me, they took out our instruments and recorded this particular sound on this piece of equipment. Well, guess what? It's not working. So another technical issue today. Basically, the sound was much like the mechanical looseness that we heard before, and you can see in the spectrum there that what we're getting is some vibration coming from these big harmonic peaks here, and that's from again the vibration that was occurring in there. But look what's in between those things was 120 hertz showing up. That 120 hertz on that dry transformer again indicated that there was a core issue in there. In other words, there was an issue with the core that was causing the vibration. Note the lack of content in between as well, the harmonics. There was no content, so we knew right away it was a mechanical vibration going on, and they were relieved to hear that because they were concerned that there was an emission going on. So when they sent the recording to me, they were able to. I was able to help them diagnose. Just to make a long story short here, they were able to shut the transformer down when they looked between the windings to the core. They found that the core and the nearby windings were completely black, and they immediately removed it from service. So they were able to again be preventive, through this condition-based monitoring inspection with ultrasound, right? So from that, we were with our scanning that we do with our ultrasound, we can do reports. We can combine our reports with infrared to show infrared images. You can see these are the mechanical issues that we're showing here, but we do the same with any type of electrical asset. We can't trend electricity because electricity just is impossible to trend. It flash over can occur at any time. But with other applications, we can trend, and we use the word predict in a light way. We can do it as condition monitoring or asset management. And our reports that we can create, whether it's through the spectrum or through photos and through sounds, we can do that in our software to show that. So to surmise here, and again, I apologize for any of the technical difficulties that were happening earlier, but to surmise, what we're looking at is what ultrasound can detect and diagnose is obviously corona. We can diagnose tracking. And of course, the one that we definitely don't want to encounter, we can diagnose arcing. In conclusion, I just wanted to wrap this up in an easy way here. The safety is what we really want to preach with ultrasound. Ultrasound is a technology that should be used as a tool to help safely scan things, again, according to CSA Z463. Should be used in conjunction with infrared. And a lot of the questions I get from companies is like, okay, we have infrared. Well, what can ultrasound do that infrared can't? Here's the better answer is why not use them both? Where you should be using them both. They work off different failure modes. So that's generally the big question I have, and I generally teach that at a lot of infrared conferences and how they work together and how one thing can detect certain things and another thing can't. But what I will mention is that, again, infrared will not see corona. And infrared will not be able to tell you by looking at a hot spot. Maybe we're seeing a hot insulator. or that heat is obviously a different temperature change than the rest of the electrical assets, but it doesn't tell you if it's tracking or arcing. But what we can do is confirm that what we're hearing is corona tracking or arcing based on our spectral analysis and sound analysis through ultrasound. We can also we also determine which technology to use based on the failure modes that are happening. For example, as I mentioned before, one failure mode that we can detect that infrared can't is corona. Therefore, by doing a failure modes and effects analysis, we can look at our failure modes and go, which technology best fits that one, so we can use it in the right way. Again, using ultrasound before opening up a panel, so we can safely scan and say, no, there's no problems in there. Now we can use IR if you don't have IR windows. We definitely preach reliability center maintenance, so the proactive maintenance, preventive, and predictive maintenance. Again, when I use predictive, it's not my favorite way of saying it. I like to say condition monitoring or asset management, because when we say predictive, the first question I get from people or management is, how long is it going to last? And that's not really what we're looking at. We're looking at the early detection of failure, which is what ultrasound can do. Ultrasound is very fast and accurate on all voltages, and it can be used on all different types of systems, open systems or enclosed systems. And we do not, and I would repeat this, we do not have to open up the panel to determine what is going on behind it if there is an electrical emission. That being said, that's the end of the presentation. And again, I do apologize for some of the technical difficulties, but here's my contact information. If you do have any questions, if you're not able to get any questions in from the webinar, feel free to send me an email and or even look me up on LinkedIn and join our UltraProbe users group, and we can have a discussion. And I'd like to maybe show you a demonstration of how our equipment can work for your benefit. So with that being said, that's the end.